Have you ever wondered how a quantum computer works? Quantum computing, a fascinating field at the intersection of physics and computer science, introduces a whole new way of processing information. Unlike classical computers that we're so familiar with, which use bits represented as either zeros or ones, quantum computers operate on an entirely different level. Quantum computers use quantum bits, or qubits, a term you'll hear a lot in this intriguing world. These qubits can be both 0 and 1 at the same time, thanks to a principle called superposition. This means they have the potential to process a much larger amount of data compared to their classical counterparts. Quantum computing opens up possibilities for complex calculations that would take our current computers millions of years to solve. So, if you've ever been curious about what makes quantum computing so groundbreaking, you're in the right place. So let's dive deeper into the world of quantum computing and unravel its mysteries. The heart of a quantum computer lies in its qubits. Now, what exactly is a qubit? Well, in the simplest terms, a qubit or quantum bit is the basic unit of quantum information. It's the quantum equivalent of a classical bit that you would find in your everyday computer. But here's where things get interesting. While a classical bit can exist in one of two states, either a 0 or a 1, a qubit can exist in multiple states at once. This is due to a fascinating principle known as superposition. Much like Schrödinger's famous thought experiment with the cat, a qubit can be in a state where it is both 0 and 1 at the same time. Imagine being able to be in two places at once, doing two things simultaneously. That's essentially what a qubit can do. But how does this work? Well, without diving too deep into the complex world of quantum mechanics, think of a qubit as a spinning coin. While a classical bit would be like a coin that has landed, showing either heads or tails. A qubit is like a coin that is still spinning, representing a mix of both states. This ability to exist in multiple states simultaneously allows a quantum computer to process a vast number of possibilities all at once. A simple way to visualize this is to consider a maze. A classical computer would navigate the maze by exploring each possible path one at a time, while a quantum computer with its superposition qubits could explore all paths at once, significantly speeding up the process. The implications of this are profound. Quantum computers powered by these multi-state qubits have the potential to solve complex problems that are currently beyond the reach of classical computers. From climate modeling to drug discovery, the possibilities are virtually limitless. With this unique ability, qubits give quantum computers their edge over classical ones. Now that we have a grasp of qubits, let's talk about another key concept: quantum entanglement. Quantum entanglement is a strange and fascinating phenomenon in the world of quantum physics. It's a kind of superglue that links two particles together in such a way that the state of one is immediately tied to the state of the other, regardless of the distance between them. Imagine two entwined dancers spinning in perfect synchrony, even if one is in New York and the other in Tokyo. This is not a mere correlation, but a deep and instantaneous connection. If we were to measure one of the entangled qubits, say, to find out its spin, we would instantly know the spin of its entangled partner, even if it were light years away. This is not because the information travels faster than light, but because the two qubits are so intimately connected that they behave as a single entity. This is what Albert Einstein famously referred to as spooky action at a distance. He was skeptical of this idea as it seemed to defy our everyday understanding of how the world works. Yet, numerous experiments have confirmed that quantum entanglement is real. Quantum entanglement is a cornerstone of quantum computing. It allows qubits that are far apart to interact with each other instantly. This capability to link qubits together in complex ways is what gives quantum computers their enormous computational power. This spooky action at a distance is what makes quantum computing incredibly powerful. To perform calculations, quantum computers use something called quantum gates. Now, you might be wondering, what are quantum gates? Well, just as classical computers use gates to perform operations on bits, quantum computers use quantum gates to perform operations on qubits. However, quantum gates are far more powerful than classical gates. You see, classical gates perform basic operations such as AND, OR, and NOT. They can only change the state of a bit from 0 to 1. or vice versa. But quantum gates, they're a whole different story. They can perform complex operations due to the unique properties of qubits. Because qubits can exist in a superposition of states, quantum gates can manipulate these states in ways that classical gates could only dream of. Imagine being able to perform multiple calculations simultaneously. That's the power of quantum gates. They're not limited to just flipping states. They can rotate and transform qubits, creating a vast array of possibilities for computation. It's like having a supercharged, multi-dimensional version of a classical gate. Quantum gates work in pairs or larger groups, manipulating the states of one or more qubits to perform a calculation. They can create and manipulate entanglement, and even perform operations on entangled qubits. So, in essence, quantum gates are the conductors orchestrating the symphony of qubits in a quantum computer. They manipulate, rotate, and transform qubits to create the rich tapestry of quantum computation. These quantum gates are the building blocks of quantum algorithms. So we've taken a quick tour of the quantum computing landscape. We've started with the building blocks, qubits, which, unlike bits in classical computing, can exist in multiple states at once. This quantum superposition allows quantum computers to process a vast number of possibilities simultaneously. We've also dived into the intriguing concept of quantum entanglement, where qubits become interconnected and the state of one can instantaneously affect the state of another, no matter the distance. We've explored quantum gates, the operations that manipulate qubits, enabling us to perform complex calculations with unprecedented speed. Quantum computing is not just a theory, it's a blossoming field with enormous potential. Its implications could span across industries, from revolutionizing cryptography, making our online transactions safer, to accelerating drug discovery, potentially saving countless lives. While quantum computing is still in its early stages, its potential to revolutionize industries from cryptography to drug discovery is unquestionable. The quantum future surely holds exciting things in store for us.